Hello there. In this video we're going to discuss a couple applications of linear functions. The examples that I'm going to give are going to be primarily focused in the perspective of basic finance applications, but you can definitely extend this to anything in the natural sciences or the physical sciences if necessary. So we're just going to work through a couple applications of linear functions and pretty much explain how linear functions can be used to solve these particular types of problems. Alright, so let's start off with this first example. Let's assume that your business starts off with $500 and generates about $24 in passive revenue per hour. How much money will you have in 48 hours? So for the solution, we're going to try and model this via linear functions. So we're going to begin by letting t be equal to 0 correspond to the starting time of the revenue, which is a function of time, let's assume. And let's assume time t is measured in hours. So based on the information we have, we start with $500. That means r of t is equal to 0 should be equal to 500. So also let's see if we can figure out the rest of it. So it generates $24 in passive revenue per hour. So that means after 1 hour, we should have $500 plus $24. After 2 hours, we should have 24 more dollars than we had before, which is the same as 500 plus 24 times 2. And then after 3 hours, we should have 24 more dollars than we had before. So again, combining like terms, we have r of t is equal to 3 is equal to, let's rearrange this a little bit, so 24 times 3 plus 500. And we can continue on with this fashion. So pretty much we can generalize this for any arbitrary t, and notice that that is always going to be the same as that number. So r of t should be equal to 24t plus 500. So typically in the realm of finance, typically we refer to this term as the fixed revenue, and we sometimes refer to this as the variable revenue with respect to time t. And of course, this is a linear function because 24 is the slope and 500 is the vertical intercept b. So we have our linear model, r of t is equal to 24t plus 500. So the question asks how much money or how much revenue will we have, so r is equal to a question mark, when the time has passed is equal to 48 hours. So we've already assumed that t in our model is measured in hours, so we can just substitute 48 into the value of t everywhere we see t in our revenue model. So that means the revenue generated or in our business after 48 hours is going to be equal to 24 multiplied by the value 48 plus 500. So 24 times 48 is going to be 1152 plus 500. So that means r of 48 will be equal to 1652, and this is measured, let's assume, in dollars. So that will be the amount of revenue that we'll have after 48 hours has passed. So that's 500 plus 48 hours of 24 passive revenue. So passive revenue is really nice because you don't have to actively do anything in order to generate that. So the stock market would be a more intricate version of this. All right, so let's look at application number 2. So let's suppose that average gas prices increase linearly with respect to time if the average price in 2000, the year 2000, was 151, and the average in 2010 was, let's see, $2.96. How much will it be in the year 2028? Now, there's a lot of assumptions that are going into problems like this, especially when we talk about averages and increasing linearly with respect to time, because we have to assume that the trend stays linear in order for this prediction for 2028 to be relatively accurate. That's more of a statistics question, but let's assume, at least with respect to this application, that it is increasing linearly. So technically, the gas prices will be approximately equal to infinity if time enough passes. If enough time passes. So let's at least work with this, with those assumptions in mind. All right, so what we're going to do is this. So let's see, 2010, that's a really big number, so I definitely don't want to work with a model that has really big numbers in it. So what I'm going to do is I'm going to let t equal to 0 correspond to the year 2000. So that means the year 2010 corresponds to t is equal to 10, and the year 2000, of course, corresponds to t is equal to 0, and the year 2028 is going to correspond to the t is equal to 28. So those are relatively small numbers to work with, which is good. All right, so what do I know by assumptions? So when t is equal to 0, my gas prices, which I'm going to represent by G, so the price of gas, and let's assume dollars. So when t is equal to 0, we're given that the gas price is on average 151, so this should be actually average price of gas. And it's also given that when t is equal to 10, the price is 2.96. So we're going to construct a linear model that satisfies this criteria. Now, very important, when the value is equal to 0, this corresponds to the vertical intercept. So vertical intercept, which is b in the y equals mx plus b model. So we actually already have one of our parameters. So that means our model g of t is going to be equal to mt plus b in general. But from this first piece of information, we have the g of t must be equal to mt plus 1.51. So the only thing we need to find here is the value of m, which we can find via this. So we're going to plug this point into this model to solve for m. So g is equal to 2.96 when t is equal to 10. So let's solve this linear equation for m. So when we solve this equation for m, what do we have? So m is going to be equal to 2.96 minus 1.51, all divided by 10. So that's going to be equal to, let's see, what is that going to be equal to? About 1.45 divided by 10. So that's going to be 0.145, I believe. 1.45. So add that, yeah, that's right. Okay, cool. So that means our model for the average gas prices with respect to time is going to be equal to 0.145 t plus 1.51. So this is our linear model for average gas prices. So now we can use this model to figure out the gas price in the year 2028. So again, the year 2028 corresponds to t is equal to 28. So I'm going to take this value of time and substitute it into our model. So that means the gas price in the year 2028 is going to be equal to 0.145 multiplied by 28 plus 1.51. So 28 times that, it's going to be 4.06 plus 1.51, which is going to come out to $5.57. A bit pricey, but you know, that's what the model at least predicts. All right, so application 3. So suppose you sell X units at $5.25 per unit, and it costs 0.32 to produce each unit. If there is a one-time fixed cost of $2,500, how many units must be sold in order to break even? And what I mean by break even is you have a profit of 0, because we automatically assume or start off in debt of $2,500, so we need to produce enough units such that our revenue and our cost is equal to each other. All right, so let's create a couple functions. So our cost function is how much it costs. So it costs 32 to produce each unit, and we have a fixed cost of 25. So this is going to be equal to 0.32x plus 2,500. So again, this is our variable costs, and this is our fixed cost. And let's consider our revenue, so R of X. So what are we going to do? We're going to sell X units at 520, what is that number? 525 per unit. So 525 per unit. So that's our revenue. So from here, what do we do? So our profit P is revenue minus cost. So therefore, revenue is going to be 5.25x minus 0.32x plus 2,500. So that's our profit function. Some people use pi to represent that. So I'm going to distribute this negative and combine like terms. So 5.25 minus 0.32 is going to be 4.93x minus 2,500. So this is my profit function. So for any number of units sold X, you can figure out your profit. So I want to know my break-even points. So I'm going to set my profit equal to 0. So 4.93x minus 2,500 must be equal to 0. That means my break-even point, XB, is going to be equal to 2,500 divided by 4.93, which is equal to 507.09 exactly. But we need to round up, so round up, to figure out how many units you must sell to at least go slightly above that. So that's going to go to 508 units. So 508 units need to be sold in order to break even. But if you can sell fractional units, then you can take this 507.09 units as the exact answer. But if you can only have integer number of units, you should round up to 508. So these are 3 different applications that you can use for linear functions in order to solve real-world problems.